Check it.
Okay, let's take a look at the do now. They have equations to solve here with logarithms, and the first one has 2 logs on the left, 1 log on the right. What we'll do here is we'll combine the 2 logs on the left so that later we can drop the logs. The thing is, we can't combine the 2 logs because this 1/2 here is stopping us from doing that. So we need to get rid of this 1/2. So the way we get rid of the 1/2 is by using the power property in reverse. Instead of bringing down a power, you can also take it and put it back up here and put the 1/2 up here, which gets rid of it here. Okay, now you have this. Okay, and with this, no more numbers in the front, you can combine these 2 logs into 1 logarithm. So this becomes log base 5 of what? Oh, I'm sorry, hold on a second. This was 4 to the 1/2, right? Now, what is 4 to the 1/2? It's 2, right? So this is going to be 7 times 2, which is 14. And this is going to be log base 5 of x. And we can drop the logs now, and we get 14 equals x, or x equals 14. Now it says check your solutions. Let me be clear about something. When they say check your solutions with regards to logarithms, you're checking the domain. You're not checking to see if the right and the left equal each other. Little different of a check. So what we're doing here is we're going to take the 14 and plug it into all the logarithms and make sure the 14 doesn't crash any of the logarithms. Plugging the 14 into here doesn't work because there's nothing to plug into, so we skip it. You can't plug the 14 into here because there's no x over here either. But you can plug the 14 into this x. You'll be taking log of 14, which is fine because 14 is a positive number. So it checks out in terms of the domains, it's fine. Okay? Notice I wasn't trying to see if the left and the right side are equal to each other. That's a different kind of check. All right, let's go on to number 79. Number 79, we have 3 logarithms on the left. And what we want to do is combine all 3. Now, we can only do 2 at a time. So if we try to do the first 2, we're going to be dividing 48 by 16/5, which creates a compound fraction, which honestly I'd like to avoid. So I'm not going to do the first 2. I'm going to do the last 2. I'm going to do these first. Okay? That's going to be a product. And I'll be multiplying 16/5 times 5. What's going to happen to the 5s? They're going to cancel out. Yeah. So these 2 just become log base 6 of 16. So that's a little bit easier. I'll do that. This side is still log base 6 of 5x. And now I still have the log 48, log base 6 of 48 minus that. So now that I've taken care of that, now I can do the quotient here, this quotient rule right here, and I'll get log base 6 of 48 over 16. And what is 48 over 16? 48 divided by 16 is 3. So when I drop the logs here, okay, I'll drop the logs, I get 3 equals 5x. And flip that around and divide by 5, I get x equals 3/5. Now, check that. What I mean by check that is see if it works in all the logarithms. Well, this doesn't have an x, so I don't have to worry about it. This logarithm doesn't have an x, I don't have to worry about it. This logarithm doesn't have an x, I don't have to worry about it. But this one does. So if I put a 3/5 here, 5 times 3/5 is 3. And it's positive 3, so it's okay. It's going to work with the domain of the logarithm, so I'll box it. Now, is it possible that I made an arithmetic mistake? Yeah. I'm not checking to see if my answer is right. I'm just checking to see if the logarithm will accept a 3/5. Okay? All right, last one here, number 83. This one's a logarithm equal to a logarithm, and there's no numbers or anything outside, so really I can just drop the logs right away. So just drop the logs. And now we have this. X squared plus x equals 12. This is a quadratic, so I'll subtract 12 from both sides and get a 0 on the right side, right? So now it's in standard form equal to 0. I'll see if I can factor it. Looks like 2 numbers that multiply to give me negative 12 that add to give me positive 1 would be plus 4 and minus 3. Pretty simple. And yeah, it does work. And now I can use a 0 product rule, setting each of these equal to 0. I get x equals negative 4 and x equals positive 3. Now I have to check these to make sure that they're valid, okay? If I put a negative 4 into here, what do I get? I get a 16, right? If I put a negative 4 into here, it's still a negative 4. 16 minus 4 is 12, and 12 is a positive number, so yeah, that works. And here, there's no x to plug into, so I don't have to check this logarithm. So far, this one works in both logarithms. How about the 3? Well, if I put a 3 into here, 3 squared is 9, plus a 3, That's also a 12. That's also positive. That works there. This one I don't have to check, so they're both valid. And there you go. Now, is it a surprise that it's log 12 equals log 12? No. That actually means that the answer is right as well. But that's, not really what we're doing when we're checking logs. We're checking the domain. Okay, that was the do now. Now we're going to get into lesson 8-6. So today we're starting lesson 8-6, which is common logs. Common logs are the logs your calculator can do natively, meaning log base 10. Actually, there are two logs that most calculators will do natively. Most calculators will do log base 10, and they'll do log base this thing called E, where E is 2.71828. It's like pi. It's an irrational number, but it comes up a lot in the natural sciences. The log base E, we actually have a special name for. We call it ln for natural log. So these are the two buttons your calculator has. It has a log button and it has an ln button. Okay? And it's understood that this is base 10 and this is base E. And those are the only two buttons that most calculators have. They don't have a base 3, base 17, whatever. So today we're actually going to learn how to use the base 10 to do a lot of stuff. Okay? We're not going to talk about the ln button. This ln I usually refer to as ln. We're just going to worry about the log button. But the log button actually comes in very handy for a lot of things. Now the first thing is just taking the log base 10 of stuff. Now we've already done this before, but take your calculator and find log of 5. This is going to be base 10 because that's what log means. So I take out a calculator, I hit the log button, I put in a 5, and you want to round this to the nearest third decimal place. So I'm getting 0.6989, so 0.699. That's how you would round that. Okay? How about log of 0.3? Well, once again, it's base 10, so I use a calculator. Log 0.3, close parentheses, enter. And I'm getting negative 0.5228, so I'm going to round it as 523 rather. That's just taking logs with a calculator. Now, that's not very useful by itself. Now, it's going to come in very handy in a minute. Let's look at a problem that we started a few weeks ago, actually. When I first introduced exponentials, I introduced it to an equation 10 to the x equals 25. And we spent a lot of time trying to figure out how to solve this thing. And basically, we had to end up guessing and checking, plugging in values for x until we got 25.000. And I said to you in a recent lesson that if this was a log, you could use the power property of logs. Let's say it was log, I don't know, 10 to the x, base something, I don't know. It doesn't have to be a 10, for instance. If it's a log, you can do this. You can take this and bring it down. That's only for logs, though. That was the power property of logs. This is an exponential. It's not a log. So you may not or cannot actually take this and bring it down. There's no way to do that. So the goal here is, all right, I want to use the power property of logs. I want to be able to bring that exponent down, but I can't do that because this is not a log. Well, here's a very, very powerful thing that you can do with logs. You can take the log of both sides. If you take the log of both sides, watch what happens. I'm going to take the log of this side and take the log of this side. I now get log of this 10 to the x equals log of 25. Now that's a game changer because now I can use properties of logs. Okay? And the power property of logs is the one I really wanted to use. So now I can take this x and I'm allowed to bring it down to the front where I want it to be. So now this becomes x times log 10 equals log 25. And now, to get the x by itself, all I have to do is divide both sides by log 10. So I'll divide both sides by log 10. That goes away. X is now by itself. And I have an exact answer for x, which is log 25 divided by log 10. Now here's the thing. What is log 10? Think about it for a second. What's the base of this log? It's actually 10. So what's log base 10 of 10? 1. Yeah, so this is actually a 1 right here. So the answer is really just log of 25. I don't need to divide by 1 really, but you can do that if you want to. And you'll see it's log of 10 is 1. So what I really need is just log of 25. And log of 25 is 1.397940009. If you remember when we did the guess and check thing, that's what we got. So here it is without guessing and checking. This is exact. 1.39. Well, we're going to go to 3 decimal places, so 1.398. We'll just leave it at that. Okay? And this is huge. The fact that you can take the log of both sides and change an exponential into a logarithm suddenly opens up all of the properties of logs that we've learned and makes them available to exponential functions. Now, do I need to check my answer? No. You know why I don't need to check my answer? Because the problem was originally an exponential problem. And what's the domain of all exponentials? All real numbers, right? So that means there's no worry about not being in the domain. All real numbers means anything you got, you can stick it in here, right? Negatives, decimals, doesn't matter. So 1.398, put it in here, you will get 25 if you take 10 to that power. No need to check the answer because it's already all real numbers. So that's the thing. Let's try a couple of examples with that. So 4 to the x equals 19. All right, now, once again, this is an exponential. There's no way to bring that power down. However, now that we know we can do this, we can take the log of both sides and get this. Once we do that, we can apply the power property of logs and bring this power down. Once we do that, we have this. Now we can just get the x by itself by dividing. At this point, I have an exact answer. The answer that I want is x equals log 19 over log 4. That's an exact answer, not rounded off at all. However, you know, you're going to want to use it for stuff. You probably have to get an actual number here. So I'll grab a calculator and I'll divide log 19 by log 4 and see what I get. So this is log 19 divided by log 4. And logs tend to be irrational. So every time you do a log of something, you're very likely going to get a decimal that goes on forever and never repeats. Most of the time, they're like square roots in that sense. Okay, so I get 2.1239, so 2.14. 124 rather. 2.124, and there you go. Do I need to plug it back into the exponential? No, because exponentials have a domain of all real numbers, so you can plug anything you want into them, so that should work. Whether or not it's correct, that's a different story. But it definitely doesn't need to be checked for domain, okay? All right, that was that example. Let's go on to the next one here. Okay, so for this one, you have a power that's actually more than one term. It's not just an x, it's a x minus 3. All right, and you want to bring that power down. So we're going to use the same trick here. We're going to take the log of both sides. And that means we can take the power here, using the power property, and we can bring it down. So now I'm going to get this. I've made a mistake. Can anybody see the mistake? Yeah. No, you have to bring down the whole power, so bringing down the 3 is fine. What mistake did I make? Yeah. Yeah, see, you're supposed to take this and multiply it times the log. If I just bring it down without parentheses, I'm only multiplying the log times the 3, not times the x minus 3. So make sure you put parentheses around this entire quantity here. All right, you want to multiply this log times the whole power, not just the 3. And the way I had it without the parentheses, this was 3 times, but then this wasn't really part of that. So anyway, we have that, and we want to get the x by itself, which means we need to get all the stuff away from the x. So we need to get rid of this log 2.7. So we'll just divide by log 2.7 on both sides. That gets rid of that. And now this is x minus 3 equals whatever that is. And then we also have to get rid of this 3 here, so we'll add 3 to both sides. Okay? That'll take care of that. And now our final answer is going to be whatever we get when we put this whole mess into our calculator. Okay? But it's all base 10 logs, so we're good. Once again, you can take the log of both sides using any base you want to, but we're using log base 10. We're choosing to use log base 10 because that's what our calculator does. If our calculator did log base 2, we would take log base 2 of both sides. You can take whatever base you want. In this case, use the one that your calculator will work with. So I'm going to grab my calculator. Log of 12.75 divided by log of 2.75. Once I get that, I have to add 3 to it. So I'll just hit enter just to make sure it doesn't divide by the 3 and add 3. And what I'm getting is 5.5628, so 5.63. 5.563. Now, do I need to check my answer for domain restrictions? No, because this is an exponential and the domain is all real numbers. This next one is an inequality. Usually with inequalities of logarithms, you have to do the 3 number lines because you have to worry about the domain of every single logarithm. Here, you don't have to worry about any domain. So really, just solve it and put the answer on a number line. There's no worry about domains. Okay? Now, once again, we have exponentials here. We want to change them into logarithms so we can take advantage of the properties of logarithms that work for us. We'll take the log of both sides here, and we get log 3 to the 5y is less than log 7 to the y minus 2. Now we can use the power property of logs to bring those down, okay? And the 5y comes down times log of 3. Notice I don't need parentheses because this is all one term, so there's no need to put parentheses around the 5y, is less than, and then here I need to bring down the y minus 2. Now that needs parentheses because that's two terms. So y minus 2 in parentheses log 7. Okay, now my goal is to get the y by itself. Now there's one y over here, there's another one trapped in the parentheses over here. The only way to get this y out of the parentheses is to distribute this log base 7 like that and get a single term with a y and then move that term over. So this side is going to become y times log 7 minus 2 times log 7. This side will remain as it is. Okay, so I have a y here and I have a y here, and my job is to get them all on one side. So what I'm going to do is subtract this term right here to the other side. Now it's gone from there, and I get this. Now here's the thing. There's a y here, there's a y here. These are not like terms. I cannot add them together, so I might be at a loss for how I can get the y by itself. Well, the trick here, whenever you have a situation like this, you have a y here, is to factor out the y. If you factor out a y, well, there's only going to be one y left, and everything else will be in this set of parentheses here. So if I take a y out of here and a y out of here, all that's left is 5 log 3 minus log 7. The right side is going to remain the same. Now what I can do is divide both sides by the stuff in the parentheses. If I do that, I get y is less than this stuff right here. Now, you can leave the negative in the numerator, or you can put the negative in front of the fraction. I'm actually putting it in front of the fraction here like that. So the top is just 2 log 7, and the bottom is 5 log 3 minus log 7. And that's an exact answer right there. There's no rounding there. If I really wanted an accurate answer, like I do in AP Calculus, I ask them to give me exact answers, they would stop here. But we do want to kind of round, it says here round to the nearest thousandth, so we will go to decimal, we'll grab a calculator and put this in here. Just be careful how you do it because you might do this wrong. So you want to make sure your denominator is in parentheses in the calculator. So this is how I will do it. I'm going to ignore the negative and put the negative on myself after I'm done. So I'm just going to worry about the fraction here. So the numerator of the fraction is 2 log 7. Put that in parentheses. And then divide by the denominator, which I'll also put in parentheses. And this one's more important to put in parentheses than this one is. All this stuff here. So 5 log 3. Now 5 log 3 is 5 times log 3, but the calculator knows what I mean. I don't have to put times. 5 log 3, it knows is 5 times log 3. Minus log 7, close parentheses on the numerator and the denominator, and I'm getting 1.097, but don't forget there's a negative there that I kind of left out in my calculations, so it's negative 1.097. So y is less than negative 1.097. That's my answer. My number line will simply be that number, open circle to the left. Do I need to do other number lines for domains? No, because the domain is all real numbers for any exponential, so I'm done. Okay, this last thing that's coming up is called the change of base theorem. Now, the change of base theorem is actually a hack, in a way. It's a workaround that's going to let your calculator do bases that are not base 10. So I've just spent a lot of time talking about how your calculator does log base 10 and log base e only. Well, the change of base formula actually lets you do logs that are not base 10 and base e. It lets you do any base you want. Okay, and this is how it works. If you have a log, for instance, log base 8 of, 14, log base 8 of 14, okay? That would be your log base a of n. This is equivalent to just taking the log of the big number with any base you want to. So any b you want to, that's why there's a b here, and divide it by log of the little number down here, which is in this case 8, and once again with any base you want to. Well, both of these have to be the same base. Now, if I'm using a calculator, what base do I want that to be? I want that to be a 10, right? So the change of base formula is taking this base 8 logarithm and allowing me to change it to any base I want to. And of course, I want to use the base that my calculator understands. So I'm going to change these both to base 10, which, by the way, is the same as not writing a base at all, but I'm just writing it here to show you it's base 10. So that means I can just take my calculator now, divide log 14 by log 8, and I now have the log base 8 of 14. So that's all I have to do there. So log 14 divided by log 8, and I get an answer. I get 1.269. Okay, so I just took the log base 8 of 14. I thought the calculator can only do base 10. Yeah, it still can't do anything other than base 10, but I was able to change the base of this from 8 to 10 using the change of base theorem. Okay, and that's the idea here. Now, how can I prove that this is actually working? All right, the proof of this, if I wanted to prove to you that this was working, what I would do is say, all right, let's say I had log base 8 of 14 and I set it equal to x. I'm going to change this to an exponential by taking, the circular method here. This to the this equals this. So that means 8 to the x equals 14. And now from here, I'm going to take the log of both sides, which we learned we can do today, right? Take the log of both sides. Log of 8 to the x equals log of 14. Now, using the power property of logs, I can bring this x down like that. And now I get x log 8 equals log 14. Divide both sides by log 8, and I get log 14 over log 8. Now, what did I start with? I started with x being this thing here, right? So I've just proven that log base 8 of 14 is the same thing as that. And I've proven the change of base theorem, because the truth is I can do this with any set of numbers and it still works. So the change of base theorem does work, okay? And the way to prove it is what I just did here. So it does work, and now we can use it for some stuff, okay? Let's evaluate a couple of logarithms that your calculator can normally not do. Okay, try example 5 here. Change this into common logarithms, meaning base 10, and then let your calculator tell you what it is. Okay, so using the change of base theorem, what we're going to do here is log base 3 of 20 just becomes log of any base I want of 20 over log of any base I want, has to be the same base, of course, of 3. So basically, you're taking the log of the big number and dividing it by the log of the little number. And you get to do this with either, base 10 logs, which your calculator can do, or if you have a ln button, you can also do it with natural logs. It doesn't matter what log you use. If you use log base 2 of 20 over log base 2 of 3, it'll still work. You'll still get the same answer. It doesn't matter. So taking our calculator, what is log of 20 divided by log of 3? Well, here we go. Log 20 divided by log 3. I get 2.7268, so 2.727. 2.727. Now, let me try this with the other log button, just to see if it works. Let me try using the ln button, which is down here. There's ln, okay? And if I did the same thing, ln 20 divided by ln 3, just to prove to you whatever base you choose doesn't matter, I get the exact same answer. Now, these are the only two logs that the calculator can do. If I could do log 14, base 14, I would do it, and it would be the same answer. So change the base theorem lets you change to whatever base you want to, in this case, base 10 or base E, and it works, okay? All right, let's try the bottom one now. The bottom one is log base 6 of 8. So we're going to change that into log of 8, common log of 8, over common log, which is base 10 of 6. And like I said, that will work no matter what. And what I'm getting is 1.1605. So that's 5 or greater, so we make it 1.61. 1.161. And that's that. Okay, we're done. See you at the next video.
Check this.